Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to close your eyes for a second. Well, don't do that if you're driving, but if you're safe, close them. And I want you to picture the Earth, not a map, not, a globe sitting in a classroom. I want you to picture that view from space. The blue marble. What is the one thing that just dominates that image?
It's the water.
It's the water. It's not the continents. It's not the clouds. It is that deep, overwhelming blue.
It's the defining feature of our existence, really.
It really is. I was just standing at the beach last weekend looking out at the Pacific, and it hits you. The sheer volume of it all, 71% of the surface.
Right.
It drives our weather. It shapes our geology. I mean, it makes up most of your body weight. We are, for all intents and purposes, water creatures living on a water planet.
We are Carl Sagan's pale blue dot. And, without that water, we're just another cratered rock spinning in the dark. We're Mars.
Exactly. And because it is so fundamental, so absolutely non-negotiable for life as we know it, you would just, you'd assume that by now, by the year 2026, we would have the origin story of water completely locked down. You'd think we'd have the receipt for every single drop in the ocean.
It seems like a reasonable assumption, yeah. It's the most important substance we have.
Right. But here is the thing that absolutely blew my mind while I was reading this research packet. We don't. Or rather, the story we thought we knew, the one I definitely learned in high school earth science, might be completely wrong.
It's not just wrong. The new data suggests it's mathematically impossible.
It is a very bold statement.
It is. But that is what the data is telling us. We are looking at a brand new study published literally yesterday, January 25th, 2026, in the Proceedings of the National Academy of Sciences. It's a study that takes a look at some very, very old rocks.
Rocks not from Earth.
Not from Earth, no. And it completely upends our entire understanding of how Earth got its oceans.
And what's so wild is that to figure out where Earth water came from, they didn't look at Earth rocks at all. They looked at the moon.
They had to. It's the only clean witness we have.
Okay, we are absolutely going to get into why that is. We're going to talk about a team led by Dr. Tony Gargano. It's this massive collaboration with the University Space Research Association, the Lunar and Planetary Institute, NASA, JPL, Scripps.
The heavy hitters.
Basically, the heavy hitters of planetary science, yeah. And we're going to unpack why their findings, based on a few handfuls of dust, are forcing us to rewrite the history books.
And maybe even more importantly, why this rewriting of history might actually be the key to our future in space. It's this incredible twist.
It's a total double-edged sword, right? It's bad news for the old textbooks, but it might be great news for future astronauts.
Absolutely.
But before we get to the future, we have to deal with the past. We have to understand the story that we're now tearing down.
The standard model, as it were.
Yeah. So walk me through this, because I remember learning about the late heavy bombardment. It always sounded like a heavy metal band to me, but it was actually a geological era. What was the prevailing theory about why Earth has water?
Well, to understand the old theory, you have to understand the environment in which the Earth was born. So you have to go back in time, about 4.5 billion years.
Yeah.
The solar system isn't this polite, orderly clockwork mechanism we see today.
Yeah.
It was a construction site. It was a shooting gallery.
Chaotic.
Violent, extremely hot. You have the proto-sun igniting in the center, and surrounding it is this swirling disk of gas and dust. Now, in that disk, there's a very, very important invisible line. We call it the snow line or the frost line.
Okay, is this like the snow line on a mountain? You get above a certain altitude and rain turns to snow.
It's the exact same principle, but it's based on distance from the sun, not altitude. Inside that line, close to the newborn sun, it is simply too hot for what we call volatiles to condense into solids.
And volatiles, that's just scientists speak for things that boil easily, right? Like water.
Exactly. Water, carbon dioxide, methane, ammonia, all the good stuff for life. If you are inside the snow line, these things exist only as a gas, and the solar wind, this incredible torrent of particles from the young sun, just blows them away.
So they can't stick around.
They can't stick to the little dust grains that are clumping together to form planets. It's too hot. The stuff just vaporizes and gets blasted out to the colder outer solar system.
And Earth sits squarely inside that line.
We are well inside it. Mercury, Venus, Earth, Mars. We are the inner rocky planets. So according to the laws of thermodynamics, the building blocks of Earth, the planetesimals, they should have been dry.
Bone dry.
Bone dry. Think of a ceramic pot coming out of a kiln. There is no moisture left in there. It has been baked out completely.
So baby Earth forms. It's a molten, magma-covered rock. It's incredibly hot. It has no atmosphere to speak of, no water. It's basically a hellscape.
A dry hellscape.
Yes, but clearly something changed. I mean, I'm looking at the ocean right now. So the water had to arrive eventually. It had to come from somewhere.
Correct. And since it couldn't have been there when the planet formed, the logic, the very sensible logic dictated it must have been delivered from outside.
After things had cooled down a bit.
Exactly. It had to come from past the snow line, where all that water and ice was still floating around.
Into the cosmic delivery service.
The asteroids and the comets, specifically a class of meteorite called C-type, or carbonaceous chondrites. These are they are very primitive rocks that formed way out past Mars, out near Jupiter and beyond.
In the cold.
In the cold, yes. And because they formed in the cold, they are loaded with water. It's not liquid water, it's locked inside their clay minerals. But some of these rocks are up to 20% water by weight.
Wow, 20%. It's a very wet rock.
It's a very wet rock. So the theory, the late heavy bombardment theory, states that about 4.1 to 3.8 billion years ago, the solar system went through this massive, violent realignment. The giant planets, Jupiter and Saturn, they shifted their orbits.
And when the gas giants move, everybody else has a really bad day.
Gravity just goes haywire. They acted like a giant gravitational slingshot. They destabilized the asteroid belt. They flung billions of tons of this rock and ice inward toward the sun.
And Earth was just standing in the way.
We were in the cosmic crosshairs. The whole inner solar system was a shooting gallery. We got pummeled. And the idea was that these impacts, millions and millions of them over hundreds of millions of years, they were the delivery mechanism.
They brought the water.
They brought the water. They'd crash into the young Earth. They'd vaporize on impact, release their steam into the thin atmosphere, and eventually, as Earth cooled, that steam would condense into rain.
And it would rain for centuries.
Millennia, filling the basins and creating the very first oceans.
You know, it's such an elegant story. It's very clean. It explains everything. It explains why we have water despite being a hot planet. It explains the craters we see all over the moon and Mercury. It fits the timeline. So why has it been challenged now? Why are Dr. Gargano and his team saying, hold on a minute, that can't be right?
Well, imagine you have a theory that says a specific delivery truck dropped off a package at your house.
Okay.
You'd expect to find some evidence, right? Some tire tracks in your driveway, maybe a receipt.
Sure, some kind of proof of delivery.
That's what scientists have been looking for, the chemical proof of delivery. If these C-type asteroids brought the water, the chemical signature of those asteroids should be all over Earth's crust and mantle. We should see the fingerprints of that specific type of space rock everywhere we look.
And we don't.
We can't find them. Or, to be more accurate, we can't trust what we find here on Earth.
Why not? Is the equipment not good enough to see it?
No, the equipment is phenomenal now. The problem is the witness. Earth is a terrible witness to its own history.
Earth has amnesia.
Geological amnesia is the perfect way to put it. Think about it. Earth is active. It's alive. We have plate tectonics. The ground you're standing on right now was not there 4 billion years ago. It was deep inside the planet.
Right, it gets recycled.
Constantly recycled. It's been subducted down into the mantle, melted into magma, mixed around like in a giant blender, and then spewed back out as new lava at a mid-ocean ridge.
And on top of that, there's weather.
Oh, absolutely. Rain, wind, glaciers grinding mountains down, rivers carving canyons, and then you have biology, you have plants growing over rocks, you have bacteria literally eating minerals. Earth is constantly, relentlessly erasing its own scars.
So if a giant water-bearing asteroid hit Earth 4 billion years ago, the crater is long gone.
The crater is gone. The ejecta blanket is gone. The chemical evidence has been diluted and smeared and mixed into the great soup of the Earth's mantle over billions of years.
So asking Earth, where did you get your water? It's kind of like asking a person who's undergone total plastic surgery and had their memory erased what they looked like as a baby.
That is a very vivid and slightly disturbing analogy, but yes, it's fundamentally correct. Earth cannot tell us the truth about the bombardment because Earth has changed too much.
Which brings us, finally, to the neighbor, the silent partner in this whole cosmic dance. The moon.
The moon is the perfect control group. It's the key to the whole mystery. It formed around the same time as Earth in the same neighborhood from very similar materials, but it's small. It cooled down fast.
It died, geologically speaking.
It died geologically very, very early on. There are no plate tectonic.
No volcanoes recycling the crust.
No atmosphere, so there's no wind and no rain to cause erosion.
It's a museum.
It is a time capsule. The surface of the moon, what we call the regolith, is what Dr. Gargano in the study calls a time-integrated record. It has just been sitting there, exposed to the vacuum of space, collecting dust and debris for billions of years.
So anything that hit Earth during the late heavy bombardment
Also hit the moon.
because we're right next to each other. We're a system.
In cosmic terms, we are holding hands. If Earth got showered with these water balloons, the moon got splashed too. But unlike Earth, the moon didn't wipe off the water. It kept the chemical residue of everything that ever hit it locked in its surface layer.
Okay, I want to pause on that word you used, regolith.
Yeah.
Because when I look at the footage from Apollo 11, Apollo 17, I see the astronauts hopping around in this gray stuff. It looks like dirt. It looks like fine gray powder. Is it dirt?
A geologist would have a fit if you called it dirt, and for good reason. Dirt, or soil, on Earth is an incredibly complex thing. It has organic matter, it has worm casings, decaying leaves, bacteria.
It implies life.
It absolutely implies a living ecosystem. Regolith is purely mechanical. It is rock that has been pulverized into dust. Imagine a single rock sitting on the surface of the moon. A micrometeorite the size of a grain of sand hits it at 20,000 miles per hour. It shatters the rock. Now, over billions of years, that happens trillions upon trillions of times. So the top layer of the moon is just this blanket of loose, jagged, heterogeneous debris. It's dust. It's tiny shards of glass from the heat of impacts. It's rock fragments.
So the team's mission then was to look at this gray powder samples brought back by the Apollo astronauts over 50 years ago and try to find that chemical receipt for the asteroids.
Yes. They wanted to see if the tire tracks from the delivery truck were there in that lunar dust.
But, and there is always a but in science, isn't there? It wasn't as simple as just putting the dust under a microscope and seeing a little label that says, made in the asteroid belt.
No, not at all. And this is where the story gets technically very difficult. This is why it took until 2026 to get a clear answer. Because the moon is a good witness, but it is a messy, messy witness.
Messy how? You just said it doesn't have wind or rain to mess things up.
It doesn't. But it has impacts. And you have to remember, those meteorites aren't landing softly. They are hitting at hypersonic speeds. They are exploding. The energy release is massive. It's like a nuclear bomb.
Okay.
When a rock hits the moon, it vaporizes itself. It melts the local moon rock. It creates a plasma plume. Everything gets mixed together in this incredibly violent event.
So it's like if I threw a chocolate bar into a blender full of vanilla ice cream and then just hit pulse for a fraction of a second.
And then you did that a million times over a billion years in random spots. The regolith has been reworked. It's been melted. It's been mixed, vaporized, recondensed. The signal of the asteroid, the impactor, is blended almost seamlessly into the signal of the moon itself.
So how on earth do you separate them? How do you unblend that smoothie to figure out how much chocolate bar was originally there?
That is the million-dollar question. And for decades, scientists use what we can call the old way. They looked for specific types of metals. They looked for siderophiles.
Siderophile. I love that word. It sounds like someone who is just obsessed with hard cider.
I wish. No, it means iron-loving. These are particular elements, things like iridium, platinum, gold, osmium elements, that chemically they bond very strongly with iron.
Okay. And why do we look for those specific elements?
It has to do with how planets form. When the Earth and the Moon were young and molten, they differentiated. The heavy stuff sank, so the heavy iron sank to the center to form the core.
Right.
And because these siderophiles love iron, they hitched a ride. They sank down into the core, too. So the crust of the Earth and the crust of the Moon are naturally very, very poor in these metals. They're all locked away deep inside the core.
Got it. So the surface is naturally metal poor.
Exactly. But meteorites, they are primitive. They never went through that melting and differentiation process. They are chemically a complete jumble. And they are loaded with iridium and platinum.
So the logic was simple. If you find a rock on the moon's surface that has a lot of iridium in it, that iridium must be alien. It has to have come from an asteroid impact.
That was the logic. It's a tracer, a chemical fingerprint. But it turns out it's a flawed fingerprint.
Why didn't it work for this study? What's the flaw?
It's because of that messy factor we just talked about, the intense heat of the impact. When an impact happens, you create this big pool of magma. And the physics gets weird in there. The metal might separate from the rock, the silicate.
Oh, right.
It might sink to the bottom of the crater melt pool. Or if it gets vaporized into a gas, the heavier metal might condense at a different temperature than the lighter rock.
So the signal gets distorted. It's not a true representation of the original meteorite.
Exactly. It's a fractionation problem.
Yeah.
You might find a rock that has a really high concentration of iridium, but you don't know if that represents the average amount of meteorite material delivered, or if you just got lucky and found a concentrated little nugget. It's too unreliable for calculating the total volume of material that arrived.
So using metals is kind of like trying to count how many people were at a party by looking at the footprints in the muddy carpet, but the carpet has been shampooed and vacuumed 10 times since the party.
That's a pretty decent analogy, yeah. The data is noisy. And so Dr. Gargano and his team, they realized that if they wanted a real answer, a mathematical hard limit, they couldn't rely on the metals. They needed to look at something much more fundamental. They needed to look at the rock itself.
You needed to look at oxygen.
Oxygen. It is the most abundant element in the lunar crust. It makes up roughly 45% of the weight of any given moon rock. You can't separate it out. It is the rock.
Okay, but oxygen is oxygen, isn't it? The air I'm breathing right now.
Mm-hmm.
How does oxygen tell you if a rock came from the moon or from an asteroid?
This is where we have to talk about isotopes. And I promise we'll keep this as painless as possible.
You better. My high school chemistry is, it's very rusty.
Think of oxygen atoms as having different flavors. The standard flavor, the one you're mostly breathing right now, is oxygen-16. It has 8 protons and 8 neutrons in its nucleus. It's the light version.
Let's call it vanilla.
Vanilla. Perfect. But there are heavier, rarer versions. Oxygen-17 has 1 extra neutron. Oxygen-18 has 2 extra neutrons. Let's call them chocolate and strawberry.
Okay, I'm with you. And I'm getting hungry, but okay. Vanilla, chocolate, and strawberry.
Every single object in the solar system has a specific recipe, a specific ratio of these 3 flavors. Earth has a very particular blend of vanilla, chocolate, and strawberry oxygen. The moon has a blend that is almost identical to Earth's, which is a clue to its origin, but that's another story.
Right.
But those C-type meteorites, the water carriers from the outer solar system.
Let me guess. They have a totally different recipe.
A totally different recipe. They have a distinct isotopic fingerprint. They are much richer in the heavy isotopes, the chocolate and strawberry, in a way that really stands out from Earth and moon rocks.
So if you physically mix meteorite dust into moon dust, you change the flavor profile of the resulting rock.
Exactly. You shift the overall ratio. You add more chocolate and strawberry to the vanilla. But wait, there's a catch.
Of course there is. Science is never easy.
The heat. Remember how the impact melts and vaporizes the rock?
Yes, the blender effect.
Well, heat also changes the isotope ratio. It's a process called fractionation. If you boil a pot of water, the lighter water molecules, the ones with the light vanilla oxygen-16, they evaporate a little bit faster. The heavy ones tend to get left behind, so the water that's left in the pot gets isotopically heavier.
So the heat changes the flavor profile, too. Doesn't that just ruin the entire experiment? How do you know if the change in flavor is because you added a meteorite or just because the rock got cooked in an impact?
This is the absolute genius of the triple oxygen isotope method. This is the breakthrough, and this is why it's so much better than the metal method. The changes caused by heat, by this fractionation, they follow a very strict, very predictable mathematical law. We call it mass-dependent fractionation.
Okay, that sounds a little scary.
It just means the change depends on the weight, on the mass. Oxygen-18 is about twice as heavy relative to 16 as 17 is, so it fractionates twice as much. If you plot these changes on a graph, all the heat effects just slide up and down a specific line with a specific slope.
Okay, so heat moves you up and down along this one predictable line.
Right, but the meteorite signal, the mixing of a different recipe, that comes from a totally different isotopic reservoir. It doesn't follow that mass law at all. It pushes the signal off the line, sideways.
So they can look at the graph and they can separate the two effects. They can say, okay, this much of the change is because it melted, but this jumps sideways off the line. That's the alien material.
Precisely. They can mathematically unblend the smoothie. They can finally, with high precision, isolate the impactor signal from the vaporization noise. It's an incredibly powerful tool.
That is just It's so clever.
It's brilliant. And they applied this high-precision analysis to a massive suite of Apollo samples from different missions, different locations, to get a really good representative average of the entire lunar surface.
And this brings us to the verdict, the bottom line, the number. What did they find when they did all this?
They found a signal, the meteorites are there, the tire tracks are in the dust. The analysis showed conclusively that the lunar regolith contains at least 1% impact-related material.
1%.
1%. Give or take. Maybe a little more in some spots, maybe a little less. But generally speaking, the lunar surface is about 1% extraterrestrial, likely from these carbonaceous meteorites.
Okay, so hearing that, my first thought is, great, that confirms it. The theory was right. Meteorites did hit the moon.
It does confirm they hit. There's no question about that. But the problem isn't the presence, it's the quantity. That 1% number, it's not a confirmation, it's a hard limit.
Walk me through the math on that.
Yeah.
Why is 1% a problem? That sounds like a lot of rock.
It is a lot of rock. But we have to scale it up. We know the surface area of the moon. We know the mass of the regolith layer. So we can calculate the total tonnage of meteorite material that 1% represents.
Okay.
Then we have to adjust for Earth. Earth is bigger, it has more gravity, so it pulls in more rocks than the moon does. There are models for that. So we can calculate, based that 1% lunar figure, exactly how much total meteorite mass was delivered to the Earth-Moon system during that bombardment window.
Right. And then you just calculate how much water would be in that mass of meteorites.
Correct. Knowing that they're up to 20% water. And when you take that total mass of water delivered and you compare it to the actual amount of water that is sitting in Earth's oceans today, the math just breaks. It completely falls apart.
It's not enough.
It's nowhere near enough. It's not even in the right ballpark.
Put it in perspective for me. How much water are we actually talking about here on Earth? It feels infinite when you look at it, but what's the number?
Well, we often say that water is just a thin film on Earth's surface, which is true relative to the size of the planet, but in absolute terms, the number is staggering. The total mass of Earth's hydrosphere, oceans, ice caps, rivers, everything is about 1.46 sextillion kilograms.
Sextillion.
That's a 1 followed by 21 zeros. It is 1.600 quintillion tons. It's a number that is almost impossible for the human brain to process.
That is, yeah, my brain just refuses to process that number.
It's a global ocean, 3 miles deep in places.
Yeah.
And the meteorite delivery rate, calculated from the hard limit on the moon rocks, it would only fill a tiny, tiny fraction of that basin.
So it's not just that it comes up a little short.
It's not a rounding error. It's like trying to fill an Olympic swimming pool with a thimble. You are adding water, sure, but you are never, ever going to get a pool.
So Dr. Justin Simon from NASA, he was one of the authors on this paper, he had a quote about this, a very carefully worded quote.
Right. He said, and I'm paraphrasing, the results don't say meteorites delivered no water. They just make it very hard for them to be the dominant source.
Dominant being the key word there. They were a sprinkle, not the main course.
Exactly. They were a contributor, but they were not the source of our oceans.
This is a huge deal. This is a fundamental shift in planetary science. Because if the water didn't come from the sky during the late heavy bombardment, where on Earth is it from?
Well, it's what Sherlock Holmes would say, right? When you have eliminated the impossible, whatever remains, however improbable, must be the truth. If it didn't come from outside.
It had to have come from inside.
It has to be endogenous.
Yeah.
It was here all along.
What does that mean exactly? Endogenous? How could it have been here all along if the Earth was supposed to be bone dry?
It means the water was part of Earth's original ingredients list. It implies that when Earth was forming from that swirling cloud of dust and gas, even though it was hot, even though it was inside the snow line, it somehow managed to grab onto water molecules and trap them.
Trap them where? Deep inside.
Deep inside the rock structure itself, yeah. Locked into the minerals of the mantle. Or another theory is that maybe the Earth formed much, much faster than we thought, and it trapped a huge amount of gas from the solar nebula before the sun's wind blew it all away.
And then what? It just stayed down there?
For a while. Then, over hundreds of millions of years, volcanoes acting like planetary plumbing burped that water out as steam. Geysers, volcanic eruptions, releasing it to the surface to form the oceans from within.
This completely changes the personality of our planet. The old story was that Earth was a dry, dead rock that just got lucky. It got saved by a convenient asteroid shower.
Right. A serendipitous accident of celestial mechanics.
But this new story, it sounds like Earth was born wet. It was resilient. It held on to its lifeblood through the most violent, fiery period of its birth. That feels different?
It suggests that habitability might be a more fundamental property of planetary formation than we thought. Maybe it's not just a lucky roll of the dice with asteroid impacts.
That is a profound shift in thinking, and it opens up a whole universe of questions about other planets.
It does, but, and here's the pivot, the twist in the story that I promised at the start. While this study is a bit of a bummer for the asteroid water theory on Earth, it is absolute 24-karat gold for something else.
For the future.
Specifically for our future on the moon.
Because even though we just said the amount of water delivered was tiny compared to Earth's oceans, tiny is a relative term, isn't it?
Everything is relative in space, 1% of the lunar regolith being meteorite material. When you do the math for the entire moon, that translates to billions of tons of water delivered to the lunar surface. For Earth, that's a puddle in the Sahara. For the moon, it's a fortune.
It's the ultimate irony. The cosmic trash that wasn't enough to fill our oceans is the treasure that's going to let us leave.
Precisely. The study confirms that the delivery trucks did arrive. Now, on most of the moon, that water is long gone. The moon has no atmosphere, barely any gravity. If a water-bearing meteorite hits the lunar equator at noon, the water vaporizes, and the intense sunlight just boils it off into space instantly.
So the equator is dry.
Bone dry. But there are places on the moon where the sun never shines.
A darkness at the edge of town.
The permanently shadowed regions. PSRs.
These are the deep craters at the poles, right?
Yes. The moon's axis is very straight. It doesn't tilt like Earth's does to give us seasons. So at the north and south poles, you have these incredibly deep craters like the massive South Pole Aitken Basin, one of the oldest impact features in the solar system, where the crater floor has been in total complete darkness for maybe 2 billion years.
It's the ultimate deep freezer.
It is a perfect cold trap. The temperatures in these PSRs drop to minus 200, minus 230 degrees Celsius. So when those meteorites hit other parts of the moon and release their water vapor, some of those individual water molecules would just hop around the surface until they randomly landed in a PSR.
And once they land there?
They stick, they freeze solid, and they never, ever leave.
So the 1% chemical signature that Dr. Gargano found in the Apollo samples, that's just the trace residue left on the sunlit surface. But in these polar craters, there could be massive concentrated deposits of ancient meteorite ice.
Layers and layers of it, accumulating for billions of years, waiting for us. And this is why every major space agency, NASA with its Artemis program, ESA, the Chinese CMSA, the Russians, they're all targeting the lunar South Pole.
It's not just for the cool view. It's for the resources. It's a water rush.
It's the great migration that the article talks about. It's about living off the land.
Okay, so let's break down the shopping list. We land there, we send a rover into one of these dark craters, we find the ice. What do we actually do with it? Obviously, number one is you drink it.
Survival. Basic survival. Water is heavy. Launching a single bottle of water from Earth to the moon costs thousands and thousands of dollars. It is the most expensive bottled water in the universe. If you can mine it there, if you can melt it and purify it, you don't have to bring it. That changes the entire economics of space travel instantly.
Okay, so we drink it. We can use it to water plants in a greenhouse for food. What else?
Radiation shielding. This is a huge, often overlooked one. Deep space is awash in radiation. Cosmic rays from distant supernovae, solar flares from our own sun. You need thick walls to protect human DNA from damage on long missions.
And water stocks radiation.
Hydrogen is incredibly good at blocking cosmic rays, and water, H2O, is full of hydrogen. So if you build a habitat and you surround it with a jacket of water, or you mix the water into the regolith to make a kind of concrete and bury your habitat under that, you create a safe haven.
That's incredibly smart. You live inside your water tank, basically.
But the killer app, the thing that really matters for the future, for becoming a spacefaring species, is fuel.
Rocket fuel.
Rocket fuel.
Yeah.
Water is H2O, hydrogen and oxygen. If you run an electric current through it, a process called electrolysis, which is high school science again, you can split it. You get oxygen gas, which you can use to breathe in your habitat. And you get hydrogen gas.
And if you chill them down until they become liquids?
You have liquid oxygen and liquid hydrogen, LOX and LH2. The most powerful, most efficient chemical rocket propellant known to man. It's what powered the space shuttle's main engines. It's what powers the core stage of NASA's SLS rocket today.
So the moon becomes a gas station in the sky.
It becomes an interplanetary depot. If you can refuel your spacecraft on the moon, you can go to Mars. You can go to the asteroid belt. You break what's called the tyranny of the rocket equation. You don't have to carry all of your fuel for the whole journey from the surface of Earth, which means you can carry more cargo, more science equipment, more people.
it connects back to the meteorites in such a beautiful, poetic way. The same bombardment that failed to give our Earth its oceans gave us the keys to leave Earth.
It's amazing, isn't it? That tiny trickle of water, frozen in the dark for eons, it could be the catalyst for us becoming a multiplanetary species.
The article also touched on one more thing that I found just fascinating: infrastructure, specifically building radio telescopes.
Ah, yes. The view from the far side.
How does water help us build a telescope?
It's about presence. It's about being able to stay. To build a massive, sensitive radio telescope on the far side of the moon, you need infrastructure. You need power, you need robots, you probably need humans to service it. You can't do any of that if you're just camping for 2 weeks at a time.
Right.
The water enables a permanent base.
And why do we want a telescope on the far side of the moon so badly?
Because Earth is loud. Electromagnetically speaking, it's screaming. We are constantly broadcasting TV, radio, military radar, our cell phones, Starlink satellites. We are blinding ourselves to the faint whispers of the radio universe. The far side of the moon is the only place in the entire inner solar system that is permanently shielded from all of Earth's radio noise by thousands of miles of solid rock. It is the quiet zone.
So if we use the water from the poles to build a permanent base, we can then build a listening post on the far side that could let us hear what? The very beginnings of the universe.
We could detect signals from the cosmic dark ages, that period of time before the very first stars ignited. We could map the hydrogen of the early universe. We could do a kind of science that is literally impossible to do from Earth or even in Earth orbit.
It all comes back to these rocks.
I
want to take a moment to appreciate the ground truth aspect of this whole deep dive.
Ground truth, yes.
We are talking about a cutting-edge study published in 2026. But the samples, the actual rocks they put in their machines, those were collected when?
Between 1969 and 1972 by the Apollo astronauts.
That is over 50 years ago. That's just incredible to me.
It is a testament to the foresight of the Apollo program. They didn't just collect rocks for the scientists of the 1970s. They explicitly curated and sealed some of these samples for the future. They knew technology would improve. They knew we'd invent instruments like these incredibly high-precision triple isotope mass spectrometers that didn't even exist when Neil Armstrong took that small step.
Dr. Gargano in the paper calls himself and his team part of the next generation of Apollo scientists.
He is. He's answering fundamental questions that the astronauts on the surface couldn't have even formulated back then. That is the incredible power of sample return. A rover on Mars is fantastic, but it's limited by the tools it carries on its back. When you bring the rock home, you can throw the entire weight of Earth's scientific capability at it for decades to come.
And it really emphasizes why we need to go back, not just to plant a flag and make footprints. We need more rocks. We need different rocks.
We desperately need rocks from the poles. We need rocks from the far side. You have to remember the Apollo missions all landed in a very specific, relatively safe zone, the equatorial near side.
The easy zone to get to.
The easy zone, basing our entire understanding of the moon only on the Apollo samples, is like trying to understand the geology of the entire Earth if you only ever landed in the Sahara Desert. You'd miss the rainforests, the ice caps, the Himalayas, the deep oceans. We need to diversify the collection to really, truly nail down this water story.
So let's bring it all home. Let's synthesize this for the listener who is trying to file this away in their brain, because we've gone from the ancient past to the distant future.
Sure. Let's do a quick recap.
Okay, point one, the old story. We used to think Earth formed dry and got all of its water from a massive asteroid storm called the Late Heavy Bombardment.
Right. The Cosmic Delivery Service.
Point two, the investigation. Dr. Gargano and his team used a new, very clever method, triple oxygen isotopes, to separate the heat signal from the meteorite signal in the Apollo moon rocks.
And they found that the meteorite signal is real, but it's small. Only about 1% of the lunar surface is made of this stuff.
Point three, the math failure. When you take that 1% and you scale it up to Earth, it is mathematically impossible for those asteroids to have filled our oceans. There just weren't enough of them.
Which forces us to a new conclusion. Earth's water is likely endogenous. It came from within the planet itself.
And finally, point four, the silver lining. That same trickle of meteorite water that was useless for filling Earth's oceans is now sitting concentrated as ice in the lunar poles, waiting to become the drinking water, radiation shielding, and rocket fuel for the next generation of space explorers.
That's a perfect summary. We lost a simple, elegant origin story, but we gained a practical roadmap to the stars.
I think I'll take that trade. But before we sign off, I want to leave everyone with one final thought. Something that wasn't explicitly in the paper, but has been nagging at me since I read it.
Let's hear it.
We spend so much time and energy looking for Goldilocks planets. Planets that are in the habitable zone, just the right distance from their star to have liquid water on their surface.
Right. The habitable zone. It's our primary target in the search for life.
But this new study implies that just being in the right place might not be the whole story. If Earth didn't get its water from a lucky asteroid strike, if it held onto it because of something intrinsic to how it was formed, what does that say about all the other planets in the universe?
That is the big question, isn't it?
Does it mean that wet planets like Earth are actually common because water is just baked into the recipe of planetary formation from the start? Or does it mean that they're incredibly, impossibly rare because holding on to that precious water while being blasted by a violent young sun is a miracle of physics?
It shifts the variable for life. It suggests that life might not depend on a lucky rock throwing water at you, but on how robust the planet's embryo was to begin with, how well it held on to its inheritance.
Are we common? Or are we a miracle of retention? I have a feeling the answer to that question is waiting for us, frozen in the dust of those dark craters at the south pole of the moon.
I think you're right. We just have to go and dig it up.
We will be watching. Thank you so much for walking us through the isotopes and the sextillions and everything in between. It's truly amazing how a pile of old gray dust can change everything we thought we knew about our own blue marble.
It was my pleasure. It's always good to re-examine the neighborhood.
For everyone listening, thanks for diving deep with us. Keep looking up, stay curious, and we'll catch you on the next one.
Goodbye, everyone.
See ya!